We'll start where we left off last time. I think we were talking about the voltage doublers, correct? Right? So, can somebody explain to me what these voltage doublers do and how they operate?
Basically, while one's charging, the other's discharging along with the power output, so it's doubling your power on that one, the top one. Second one, it matters if the switch is closed or not, whether
Sure.
or not it's going to be double or same.
So, in the top one, there's no switch, right? So, in the positive half cycle, in the first half cycle, D1 is on. If D1 is on, then current is flowing from my source through D1, charging my capacitor. Okay. Some of the current is, so some of the current is charging my capacitor, and then some of the current is also feeding the load, right? And then current can come back through here. That's the current that's coming from the source, and since I have a closed loop here, this capacitor current is also used, or the voltage that you've charged this capacitor to was also used to supply this load with current as well. So there is current as well flowing from inside this loop, right? So this is a closed loop as well. As soon as you have voltage source in a closed loop, current will flow in that closed loop as well, yeah. Right? So that's in the positive half cycle. So in the positive half cycle, this is charging, and if this has any charge on it from the previous cycle, then it will help or aid in that current flowing in this loop here, right? And in negative half cycle, what's happening? In the negative half cycle, current flowing out of the source here, charging this capacitor back through this diode to the supply. And then we have the same thing. This is a closed loop, and this has voltage, and now this one has voltage from the previous cycle. So I have voltage sources, two voltage sources here, with a resistor across them. So there will be current as well flowing to the load, right? The limitation is this load cannot be too high. It's like the capacitive rectifiers that we discussed before. If you don't choose the proper size capacitor or proper size bucket, and you're taking too much water out of it at the same time, then the level will fall down very quickly, right? So, and it's the same thing here. You're basically charging this capacitor to a voltage level, and you're drawing a certain amount of current out of it. The size of the capacitor depends on how much current you're drawing out of it, and that's, remember how we were sizing capacitors, right? We were drawing the current waveform, capacitor current waveform, and then the area under the current waveform was charge. So we were able to size the capacitor based on charge, the specification of delta V that we want, so the change in level of water, right? For these two variables, we were able to calculate capacitance, right? C was equal to delta Q over delta V, right? So that's the top circuit. The bottom circuit is very, very similar when the switch is closed. When the switch is opened, it's a full wave rectifier. Same full wave rectifier circuit that we discussed before, and we discussed the full wave rectifier with a capacitive output filter. That's exactly the same as this circuit when the switch is open. Exactly the same, identical. Okay? It's just that we have two capacitors instead of one, so the voltage is divided between the two capacitors. The output voltage is divided between the two capacitors, yeah. But when the switch is closed, it behaves like this circuit here. So in this circuit, I can create 2V maximum only. In this circuit, when the switch is open, the output can have a maximum voltage of V maximum. When the switch is closed, it can have a voltage of 2V maximum. And the way it operates is similar to here. So in the first half cycle, current flows through diode 1, right? And then reverse bias is diode 3, right? So the reverse bias means, because I'm putting the positive terminal here, I'm reverse biasing diode 3. I'm charging C1, and then current is going back to the supply, right? What else? And if initially in the initial condition, this capacitor is not charged either. So this current that's coming back here, if this capacitor is not charged, And if this is an ideal diode, meaning no forward voltage that opposes the flow of current, right, then current can also come back through here in the first half cycle. So you see why? Do you see? I mean, this is the way you can go back to the supply. So current will follow the path of least impedance. If this is a capacitor that's an ideal capacitor and doesn't have a voltage across it, so it's not charged, so it's not opposing the current flow, right? And then this diode is ideal, right? So there's no drop across it, and there's no forward. So yeah, there's no forward drop across it that's opposing the current flow. Then for the current, this path is the same as this path, right? So that's why in the simulations, I will zoom in on something. Yeah, I will zoom in on here in the next slide, right? And then you will see diode D2 current. There will be some current through D2 flowing. There will be some current flowing through D2, and that current is equal to the capacitor current, right? The load current. They're both equal. The paths are the same, have the same impedance, so the same current will divide up between both of them, right? But only initially. Then this D2 current dies away. Why does it die away afterwards? Because then this capacitor charges. If this capacitor charges, if C2 charges, what happens? And this switch is closed. If C2 is charged and the switch is closed, can current flow through D2? It reverse biases D2, right? If this is charged, plus here, minus here, you're putting current through into the capacitor, it will reverse bias D2 after the first initial transient. And then D2 is always reverse biased after that, right? So that's why I zoomed on it here only in the first initial transient. If you do the simulation, you will see that. Only in the first initial transient, you will see this red current, the diode current, diode D2 current. Other than that, it's reverse biased as soon as you start charging the capacitor. So I start charging this capacitor in the second half cycle. So in the second half cycle, this capacitor is now being charged through here, right? So the current is flowing out of here, out of the source, into C2, charging capacitor C2, back through diode D4. Okay? But initially, just for a transient, which we don't care about transient, but I just wanted to, if you simulate it and see something like that, you're going to say, okay, what's going on, right? So I wanted to help explain it at the beginning. But if you do it in your simulation and put an initial voltage on that capacitor C2, even if that voltage is 5 volts, 2 volts, it's still going to reverse bias D2, and it will impede the flow of current coming through from the first half cycle. It will be an impedance, so most of the current will not actually go through there at all. Actually, none of the current will go through there because the capacitor C2 is reverse biasing D2, as well as this capacitor has a voltage across it that's opposing the current, right? So this is sort of all the transient stuff that's happening in the circuit. But in steady state, what we're doing is first half cycle through D1, we're charging C1, right? And then second half cycle through D2, we're charging C2. Through this path, through C2, and back through D4, we are charging C2. Okay, so in the first half cycle, we're charging C1 through D1, and the second half cycle, we're charging C2 through D4. Everybody's okay with this? Okay. And it operates exactly the same way as the capacitive rectifiers, right? So in steady state, this capacitor has a voltage across it, right? In the positive half cycle, we've charged it to what? We've charged it to a peak voltage V maximum, right? And then what's happening? Then fine, its voltage is dropping slowly because it's part of this circuit here, and it has to supply this resistive load, right? So, but its voltage is dropping slowly. We switch to the second half cycle and charge C2. Then we go back to the positive half cycle. C1 has some voltage across it, right? So will D1 start conducting as soon as we hit the next positive half cycle? It won't. Why? Because the voltage across the because there is voltage across the capacitor. It's like the R and the source circuit that we discussed before. it will only start conducting when the source voltage is greater than that DC voltage that you're trying to, that's opposing you, right? So that means that that the diode D1 will conduct only for a short period of time. And what is it doing for that short period of time? Dumping as much energy as possible into the capacitor to charge it, right? So that's why you will see these current peaks similar to the capacitive rectifier that we've seen before. For one half cycle, it will be the blue for one capacitor. For the other half cycle, it will be the red for the other capacitor, right? And if you zoom in on here, you will see one capacitor is charging here. That pink is rising, right? And then it just keeps decreasing, 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 decreasing until the next negative half cycle. And then the green is the opposite. It charges up in the positive half cycle and then keeps decreasing until the next positive half cycle. You okay with this? Please simulate it, please. Simulate it, and you will understand it a lot better when you simulate it. Zoom in and see what's happening. It will. I mean, you will understand it a lot better. If you don't understand it yet. Why is it not going away? Okay. So I talked about this diode D2 initially conducting until C2 is charged, and I zoomed in on it down here. And again, we see in both circuits, the output voltage is this red one, and it's a sum of the two capacitor voltages. So I made one in positive blue and then one in negative, just so that we see them both and they're not superimposed. Right, so one of capacitor voltage is here, the other capacitor voltage is here. So this charges up in the first half cycle. Right, the capacitor starts charging in the first half cycle to V maximum only. Right, it does not go to V maximum initially. Right, because initially we're charging the top capacitor only. So the output voltage can only reach V maximum, and then after that, in the second half cycle, we can reach 2 V maximum. Okay? Yes? No?
Yep.
So that's this stuff. Okay, so what we see here, if we look at the current waveforms, again, we understand now that this current waveform is the source current, right? And it's the time when the diode, the corresponding diode that's connected to the capacitor is charging. And is connected to the supply to charge the capacitor. And that's why we know that capacitor current can change instantaneously. That's why we see these large jumps, right? Why are these large jumps occurring? Because IC equals C dVC by dt. The capacitor voltage was dropping, right? And because it was dropping and it became a little less than the source voltage, we wanted to charge it. And so the diode connects. As soon as the diode connects, we are instantaneously trying to change the slope of the voltage, right? So we are quickly trying to change the slope of the voltage. So if we change the slope of the voltage to try to charge up the capacitor again, then IC, which is equal to C dVC by dt. So the dVC by dt is something that's changing very quickly. So because it's changing very quickly, we see this huge jump in current initially. So it's a large value of current. And then what's happening? The capacitor is charging. When it charges, it's rising up to the supply voltage, right? So initially it was a certain slope, right? So we had a capacitor was discharging all the capacitor type circuits. So the capacitor was, let's say, it was discharging. It charged to the maximum voltage here, and then it was discharging until the next positive half cycle. Here, what did we do? The capacitor voltage, which is this waveform, the red waveform, became less than the source voltage. So its slope was like this. Now I want to change its slope from this negative slope, drastically change it to a completely different slope. So the slope was here, I completely change the slope to a completely different value. Right? So I significantly change the slope. So if I significantly change the slope, I know the capacitor Current is IT equal to C dVc by dt, and this is the slope of this waveform. I've changed this voltage significantly. I wanted to change it significantly in a very short period of time, right? This is a very short period of time. I changed this voltage significantly in a short period of time. That means I have a huge inrush of current. This inrush of current will happen here, right? It will occur at this time, and then what's happening later? Then the slope remains the same, and it changes slowly until it reaches zero, right? So then the current falls down to zero and changes slowly, right? So you will see these. This is typical capacitor charging waveforms. Yeah. So this is something we see in the circuit. What's bad about this?
Bad about it?
Yeah, what's bad about this current waveform? If you remember stuff from chapter 2, we took some, we learned some stuff about RMS, peak values, crest factors, total harmonic distortion. So obviously this is not a sinusoidal waveform, right? So there's a lot of distortion there. The other thing is, what is power? How do we deliver power? You remember, at the end of the day, we're taking power from the source. We want to deliver to the load, right? So if you remember the calculations for power, we multiply the fundamental voltage by the fundamental current. And any harmonic voltage by the corresponding current, right? And here we have the voltage at the input is what? Our input voltage is this waveform. It's a nice pure sine wave. How about the current? About my current? Current is used to charge this capacitors, right? So I have one positive, one negative. This is, here in this case, this is capacitor current. But if I draw the supply current to be one positive spike, one negative spike. Same as the capacitor current, right? One positive spike, one negative spike. We went through that for the capacitive rectifier, right? We one positive spike, one negative spike. One positive spike, one negative spike. This is not sinusoidal. Our voltage is sinusoidal. What does that mean? That means I have a lot of current harmonics, and I have a fundamental voltage only. So I have a lot of current harmonics that are not useful for delivering power. Correct? And they have very high peaks compared to the area under them. The area under them is sort of proportional to the RMS value, right? So when we calculate the RMS value to calculate power, power is equal to VRMS, IRMS, cosine the angle between them, right? So the RMS is what? Root mean square. It's sort of proportional to the area under the curve, right? So I can get this same area, right, by flattening up the curve. If I have a way to flatten up the curve, I can get the same area, at the same time reduce the peak, right? I mean, if I have the same area, that I want to take this area and flatten it out. Is that good or bad? It's probably good, because I don't have the same peak currents flowing through my devices. So my devices can be rated for less peak currents, right? And I can get the same amount of power transferred, right? So that can be, and then you would, again, these significantly high jumps in current indicate what? Like impulse functions, lots of harmonics, right? So then you have a lot of components in current that are not useful to generate power. But if you flatten it out, you don't have this impulse thing happening at all. What happens? The frequency of the harmonic spectrum of the current decreases, right? Then you're better off. You're also better off because the peak currents in the devices decrease. Peak currents in your cables and power supplies and your boards and etc. They also decrease, right? So that's a good stuff. That's a good thing for you. So how do we do that in these kind of circuits? How do we do that in all these voltage doublers as well as this capacitor rectifier? This capacitor rectifier is the same, right? Anytime we are charging the capacitors, we see this huge jump in current and then decay, right? And that's affecting my source current, right? We drew the source current last time. It was these spikes, one positive, one negative. So how would what do you think is a way to mitigate this issue and still, get the same sort of output voltage that I want? Sure, right? So if I add an inductor here in the path, it's okay if you looked at the slides, it's fine. If I add an inductor in the path, in the series path here, so what will happen? If you look at what's happening on this.
So we're going to do RLCs.
Excuse me?
Like you said, we weren't going to do RLCs.
No R's. our filters are always reactive elements, LCs. This is my load,
Oh, okay.
right? So this capacitor was like a first order filter. Now I have a second order filter. I can add higher order filters as well. I mean, we'll talk about that later. But this is an example of what we can do. If you put this inductor in series, what's going to happen to the currents? I mean, the current that we had in this circuit that was going into the capacitor looked like what? Or, that was going to the capacitor looked like these spikes, right? It looked like these current spikes. But if I put an inductor through there, an inductor does not allow current to change instantaneously, right? So the capacitor wanted to draw this kind of current, these spiky currents from the supply. I put an inductor in series. If I put an inductor in series, then it limits the rate of change of current. So I no longer have these spiky currents, but I'm delivering the same RMS power, the load power to the resistive load. Right? My load is not going to change. My load still requires 10 watts, for example, right? But I've added this inductor in the middle. So fine, it will add some losses. The inductors the inductor is basically a piece of copper wire that has a resistance, right? So there will be some resistive loss or some efficiency penalty that you will, but you get this efficiency penalty, but you have a much better waveform for input current and potentially for the output voltage as well, right? So it's something that you would have to do the calculations for, right? So it's yes, sir.
Right. How do you just choose when the inductor to be there? Like, why couldn't it be with in series with the capacitor across the resistor? You know what I'm saying?
Yes, but if you put it in series, then the combination is either an inductor or a capacitor, right? So depending on the values, the combination will either be an inductor or a capacitor, or it will be inductor or capacitor in a certain frequency range, right? You've studied resonance, series resonance, parallel resonance. You've taken these circuits, right? So in 214 you did not. Yeah, you have to.
Way too long ago.
For me, it was even longer, right? And I never taught 214, but I mean, the idea of series resonance is a very important phenomenon, right? Because I mean, if you are able to design a circuit that behaves like a short circuit at a certain frequency, you can do a lot of stuff with that. That's a nice filter, right? If you have harmonics in your power system, so that's if you have a big drive, if you have a big power electronic load here that is consuming these spiky currents, right? And these spiky currents, assuming we were able to add some inductance and sort of smooth them out a little bit, right? Then they are occurring at, maybe the fundamental frequency and maybe a few other frequencies. So if I'm able to design some resonant circuits that I place across here, what's going to happen to any harmonic currents that this load is going to try to consume? They will be supplied. They will be shorted out by this. So this is like a short circuit for any current that's a certain frequency. So if this load is trying to draw a certain amount of current from the source, this impedance here can shunt down that frequency. It looks like a short circuit to that impedance only. Only that frequency of that supply volt or only that frequency of current. This circuit will look like a short circuit to it. So the supply will no longer supply that. If it's something that's required by this drive here, or being generated by this drive, right? It's not being generated by the source. It's being generated because of the circuit that I have in the drive. As soon as I put this harmonic filter, I have a zero impedance at that frequency. If I have a zero impedance at that frequency, that current can never come from the supply. It can never come from the supply. It will flow here. It can flow through this circuit here. I have a harmonic source here at a certain frequency, 150 hertz. This is a zero impedance to that source. It's a zero impedance to that source. So these harmonic traps are used. They're very commonly used in industry, actually, right? So you can put it in series, and there's a reason to do it. And you would do that typically for filters. And you typically put a resistive circuit as well in there, because a resistive element in there, because if you, I mean, temperature changes, you're maybe not able to tune the circuit to your exact frequency. So you want to be able to also burn some of the power loss in case that the frequency, deviates a little bit. Yeah. But the objective of this inductor is to add a second order filter, create a higher order filter to be able to filter more of the components. Okay. How do you size this? We talked about sizing inductors last time, right? So an inductor, for the inductor, you would size it to minimize what? Current ripple, right? So initially, what did my current look like? This big spike here. Now, what does my current look like? Something with a lot less ripple, right? So there was a delta I spec that you had to come up with. I wanted to make my ripple 2 amps or 5 amps or whatever. And then what did I have to do? I had to calculate the voltage, right? The L was equal to what? The amount of flux linkage that I've added in one cycle divided by the amount of what? L is equal to delta lambda over delta I, right? So delta I delta I was your spec. If you remember from the last class, we were sizing inductors and capacitors. We said that C was equal to delta Q over delta V. And this was a spec. I wanted delta V to be a certain value, right? That's this, these two things that, okay? This was my original delta V, right? This was the full delta V originally. And now this is my new delta V. Right? This is my new delta V. And that's how I size my capacitor. This is a spec. This is not after the fact. This is something you design because the load requires that. Right? So that's how you would size a capacitor. If you look at the current flowing through the capacitor, calculate the amount of charge you put in or out. Right? Not because the amount of charge you put in and out, they should sum to 0, right? Plus and minus, they should sum to 0, because at steady state, you want to maintain capacitor voltage, or at every periodically this capacitor voltage will come to the same value, right? At here the capacitor voltage is the same as here, right? This is a periodic waveform, right? But the average value will not change. And similarly, inductors, delta lambda over delta I. Delta I is a spec, right? I had my current spikes looking like this. Now I change so this was my delta I originally. And now my current waveform looks like this. This is my new delta I. Right? So given my delta I, which is a spec you designed for, and looking at the voltage across the inductor, you should be able to calculate the value of inductance. We will do a lot of that later in chapter 6, but it's good to refresh your mind as well of what we did last time. Okay, so that's this. These are some of the output voltage waveforms.
Which,
yes.
that bottom one?
This one?
No,
Yeah. What's the difference between these two?
The second graph. No.
What?
On the next slide.
Ah.
That one.
Okay, so let me.
What's that a relationship of?
Yeah, I'll show you. So these two, let me just do this first. So this is inductor current. This is inductor current as well. But what we did here was we increased the load current. So what I did was reduce the value of R so that the average load current increased. The average load current increases. What will that do to IL? That means the average value of IL will also increase, right? But the ripple content will remain the same. So the amount of ripple is something you designed for. If I designed for this amount of ripple current, then the ripple current in this circuit will always be this amount, right? But I can increase my average value of current. So my current can draw more average current, right? So even though my ripple content, so if you look at the ripple content here, fine, here it's because it's discontinuous. But if you increase this, if you make this continuous, the ripple content will never change. Right? So the ripple content will not change unless you change duty. Here there's no duty cycle change, but we'll look at that more in chapter 6, where some ripple can change as well. Yes.
So I thought that the kind of waveform that you get in B is the one you get when your inductor value is large, because isn't the difference between continuous and discontinuous?
The inductor value is large, or the load current is large, right? Remember when we were doing the rectifiers and we with the opposing with the source, it was both the inductor value and the source value that were changing the position where the current would become extinct, right? So it's if I increase my inductor, I can make the current continuous, but I cannot create an average value out of nothing, right? I mean, it's capacitor consumes zero average value. There's no average value of current flowing through a capacitor, right? So capacitor average current is zero. So if I have an average value, that means I have a load, right? The load is consuming my average value, but all the ripple will flow through where? All the ripple will flow through where? What's the impedance of a capacitor? Xc is equal to what? 1 over j omega 1 over omega c, right? So if c is large, very large, infinitely large, okay? What does that mean? It means that for any value of frequency, for any omega value, xc is what? 1 over omega c. If for a large value of c, any AC component will look, with the capacitor will behave like a short circuit to it, right? 1 over omega c. If c is large, omega is small. Because I have a large c, it does not really matter what the value of omega is. 1 over omega c is 0. 1 over omega c, sorry, is infinity. So the capacitor, right? No, 0, right? So 1 over omega c is 0. So 1 over omega c, if that means the impedance of the capacitor is 0. To what? To any AC component. Anytime the capacitor sees an AC component, the impedance is 0. Right? So what does that mean? That means that the AC component of this waveform, this is the inductor current waveform, correct? Here, I have my inductor here, and then I have my capacitor, and I have my resistive load, correct? This current waveform looks like what? This IL waveform looks like this, for example, initially. In one case, case 1. In case 2, what did the inductor current waveform look like? Something like this, right? This is IL case 2, right? This is a waveform that's periodic. I can use Fourier series to chop it up into an average value and AC components. So a DC value and an a set of AC values, correct? So I can chop it up into a DC value and a set of AC values, right? A set of AC components. This is flowing through here, right? It has AC plus DC, right? This is a large capacitor. So it has an impedance XC equals 1 over omega C, very large C. If it's a very large C and omega is 0, does it really matter? 1 over 0 is what? It's a very large value, right? So it's infinite impedance to what? To DC. So this, let's say now I have AC plus DC, so I can use superposition, right? So I can put an AC source and then try, and then put a DC source and try. You know, I can use superposition, right? AC plus DC. So for the DC, this will be an open circuit, right? And the DC here, I mean DC, no frequency, right? So that's the average value of this waveform here. DC is the average value of the waveform. So all the DC content, or the average value of this waveform, is going to go where? Straight to my resistive load, right? And then if I properly design my capacitor, then all the AC component will go through the capacitor, right? So no ripple. Again, you wanted to reduce ripple at the output, right? So this capacitor, ideally, if it's infinitely large, will not allow any ripple to go through. Of course, there's nothing such as infinitely large, right? That's why we have a ripple spec, right? Because you cannot put an infinite capacitor in your circuit. right? So because if this capacitor is small, then at certain values of frequency that are small, right, this impedance exists, and it's not infinitely large or infinitely small, right? It's somewhere in between. It's an impedance. So you will have current dividing up between the two branches, right? That's the real world, and that's why you have the spec, a ripple spec, because when you put a ripple spec, then most of the ripple current, most of the AC component will pass through the capacitor, but some will go through with the load. Okay? Yes, no? And the difference here is what? Here, let's look at here. If I look at here, I should see a similar delta I, similar ripple component for the same value of capacitor and resistor, right? So for the same value, but what happened was I changed my average value. My average value went up a lot higher. Why? Because my load changed. It's now consuming more current. But average value is not something that flows through my capacitor. Average value is the DC component of the waveform that I'm pushing through this inductor. It's going straight to my load in an ideal case where the capacitor is very large, right? Yes? No? You need to come and see me. Okay, so did you see the difference between these two?
Yeah.
Okay.
I was just curious what the.
So the next waveform here, so here the blue waveform is this stuff, is this inductor current waveform. The blue is this for discontinuous current case. How about the red?
It's continuous current.
No,
Oh,
the
it's
red.
reverse of it, whenever it's switched.
So what's okay? This is inductor current. Where is this being pushed into?
Capacitor.
Exactly, and the load, right? So it's being pushed to the capacitor and the load. The capacitor, can it have an average value of current? No. So what's happening is the inductor current is flowing when all the ripple component of the inductor current is flowing through the capacitor. Fine. And then what's happening? When the current in the inductor becomes zero, it's discontinuous, who's feeding the load? Here. And so the capacitor current direction flips, and I have the exponential RC AE to the minus T over tau. Same as the previous case. Do you remember the case where the capacitor rectifier that we drew before? Same. Except I don't have these spikes anymore. So now this red is the capacitor waveform, right? So this is when it's being supplied from the source, right? From my source here, current flowing through inductor, and then now this inductor current became zero. Source has been cut off. Why is the source being cut off? Because if you go out here, you will see that the capacitor voltage is now greater. The red is the output voltage, the capacitor voltage. Is greater than the blue, right? At some point here, the red is the output voltage. The red is the output voltage, which is equal to the capacitor voltage. It becomes greater than the blue, which is your supply voltage right here. So what happens is, it gets cut off. I mean, inductor current stops. Inductor current stops, and then who has to supply the load? The capacitor. So that's the capacitor. The red waveform is this red waveform here. Okay. And then here is the case where I've increased the average load current. So I've taken my load current and increased it. And this is now the capacitor current, and the red is the inductor current. As you can see, the red current here, all its AC component is going into the capacitor. Take this red waveform and filter out the DC. What's going to happen to the red waveform? It will fall, right? If you remove all the DC component, it will fall and have an average value of 0, right? So it will equal this blue waveform, right? That's then all that AC component from the inductor is going through the capacitor. The capacitor is now doing its job. It's charging to maintain its level, then discharging to feed the load, charging to maintain its level of the output voltage, discharging to feed the load, right? So that's what's happening here in this waveform. And then again, there's no such thing as an infinite capacitor. So that's why in the green, which is the output load current, you see some ripple. There is some ripple. So this red and the blue will not be identical, obviously, because some of the ripple content is actually flowing into my load because my capacitor value is not too large. When it's only infinity, well, the red and the blue waveforms equal each other. And there's no such thing as infinity capacitance. Right? So play with it, simulate it, play with the value of capacitance. and see how the current waveform changes. Any questions on this? Yes? Yeah.
Can you go to the previous slide again?
Sure.
Right. So you said the capacitor would, the inductor would stop charging
Yeah.
when the voltage across the capacitor is higher than the source.
A little across the capacitor, yes. But remember the capacitor is now behind the inductor, right? So there's a voltage drop you have to account for, right? So if I didn't have the inductor, if I didn't have the inductor, when will the D1 stop conducting? When the capacitor is less than the source, or stop conducting when the capacitor is greater than the source. When will D1 start conducting when the capacitor is less than the source, right? But now I have some impedance in the middle, right? So there will be a shift in the time at which this turn on happens, right? But it cannot happen. It will happen obviously when the capacitor, when will the inductor current cease? When the output voltage is definitely higher than output voltage plus the inductor voltage is higher than the source voltage. Okay, so I made a quick. I ate some words, right? So if this voltage, the voltage across the capacitor, plus the voltage across the inductor is greater than the source voltage, sorry, D1 will stop conducting. It stops conducting, current becomes zero.
Because I think in the graph there's a section where the first one.
This one?
Second peak. No, no.
Here?
Yeah.
Yeah.
The first graph.
Yeah.
The
This
peak before
happens, huh?
that, peak before that.
The peak before that. This?
Yeah, that one.
Yeah.
So that's the voltage across the capacitor that is greater than the source, obviously.
No, because the source, remember, this is a full wave rectified waveform. So I have to take this blue waveform and flip it up. So I have to draw it like this. No, this is what you need to look at, right? So the inductor current should fall sometime after this point, right? Because sometime after this point, the value of capacitor voltage and inductor voltage will be greater than the source, right? So inductor current will fall, right? So any questions? Good points. Sometimes I like to skim through and see who's paying attention. But I mean, the idea was the same, right? The idea is there's a voltage that's opposing that source, right? And then if that voltage is greater, then the current from the source will stop. Right? That's okay. So here, I mean, they just have a curve in the book which says, okay, so this is 3 omega L over R, this is V output over V maximum. What it's saying is basically, if 3 omega L over R increases, meaning R decreases, right? If R decreases, then what's happening to the load current? Load current becomes, the average value increases. The average value increases, I will go into continuous mode, right? That's what happened here, right? If the average value of current increased, meaning by decreasing the resistance, I will go into continuous mode. Right? They're just trying to find the relationship because sometimes, okay, not sometimes, you sometimes want to design your circuits to operate in discontinuous mode intentionally. There are reasons to do that, and we will talk about them in chapter 6. Okay, and there are reasons when you want to design your circuit to operate in continuous mode. Right? In both cases, you're supplying your load. Right? Can you not supply your load? No, you have to always supply your load. But if you're operating in discontinuous mode, that means you have these pulses of current that you're using to charge your capacitor. Then your capacitor has to be large enough to maintain the voltage across the load because you don't have any more current coming into the capacitor, right? The capacitor inductor current became zero, completely zero. When it became zero, who has to pick up the load and feed the load? The capacitor, right? That's in discontinuous mode. There are reasons to operate in that mode. You can size up the transformers and some of the power supplies to be a bit smaller. That's fine, right? So you obviously have a smaller inductor. You're operating in discontinuous mode because you have a small inductor or the load is low, right? So there are two reasons: either it's the load or the. So sometimes you want to be able to design a smaller inductor or a smaller transformer in a power supply. So you would want to design your circuit to operate in discontinuous mode. That's why they come up with these relationships between, the value of inductance, value of resistance, output voltage, etc., and talk about continuous versus discontinuous mode. Right? So it's a reason. It's a design criteria. Do you have some capacitors available. In a high temperature application, for example, I don't have very large capacitance values that can operate at high temperature. I don't, right? So since I don't have these very large capacitors values, so what do I want to do? I prefer to push myself into continuous mode, add a large inductor, because I can add these copper wires, no problem, at high temperature, right? But in a case where I'm building a power supply in Alaska, right? I can put a capacitor there, very large. I have very large capacitance values at low temperature or cold temperatures or whatever, right? But I don't want to, I would like to minimize my losses. So I don't want to put an inductor in series with copper losses that are in the way, right? So it's a design criteria. It's operating in discontinuous or continuous mode is a design criteria. Then some piece-by simulations that I would like you to play with as well. And then we go into the controlled rectifier. So we'll go through this a lot quicker. So there's the same waveform, same circuits, but we removed the diodes and added thyristors. Okay, so for the full wave rectifier circuit with resistive load, assuming all these thyristors are just diodes. If they are diodes, then our output voltage looks like this waveform, this dotted waveform, and then this continuation of it here, right? It's a full wave rectifier waveform. I made these thyristors, all of them thyristors. Then what's going to happen? These are no longer diodes. In the positive half cycle, even though I have a resistive load, D1 or S1 and S2 will not conduct. They will only conduct when I provide a firing angle or a firing signal or a gating signal, right? So I provided that at alpha. If you provide that at alpha, as soon as you provide the gating signal for S1 and S2, they behave like diodes, right? You give them a signal, they behave like diodes. If they behave like diodes, they will do what the diodes do. What would the diodes have done? The diodes would have conducted and followed and connected my source to my load. And that's what happens after a value of alpha. So in the first half cycle, we will give a firing signal to S1 and S2. Where? At point alpha. In the second half cycle, I give a firing signal to S3 and S4. Where? At point pi plus alpha. Right? And this operates the same way. So in the positive half cycle, I provide the firing signal to S1. Negative half cycle, I provide the firing signal to S2. And then everything else is the same as the diode case. Becomes a bit trickier now when you have an RL circuit. So what do you think happens in an RL circuit? Now I change this R to an L, RL. So what's going to happen? So initially nothing different, right? The circuits, they're all thyristors. I have an RL circuit here. Nothing will happen, right? Until you do what? Until you provide your firing signal. Now if you provided your firing signal to S1 and S2, right here, okay? They will behave like diodes and conduct, correct? Keep conducting, keep conducting, keep conducting, keep conducting until here. Is the output voltage going to become 0? Why not?
Because whenever your output voltage, that's going to be lagging, is it not?
What do you mean by lagging?
Well, you have your firing, whatever.
I fired 1 and 2 here.
Yeah.
And then I did not fire 3 and 4 yet. Right? I will fire 3 and 4 here. I'm asking what's happening between these two now. Exactly. Because you fired 1 and 2. So 1 and 2 behave like diodes. And I have an RL circuit. Right? Remember, if you go back to the RL circuit, with the diode full bridge rectifier, I have S1 and S2 now behaving like diodes. This is an RL circuit. Current will what? Will rise to the inductor, right? And then it will start falling. When does it stop? It will stop beyond this point. Remember, here, this is where the resistive current would have stopped, right? Where would the inductive current stop? Somewhere beyond, right? Somewhere beyond this point. So it will follow. So the S1 and S2 are diodes. They will continue to conduct until the RL circuit current becomes 0. Because as soon as R becomes 0, it's going to start wanting to flip because I put this negative voltage across it. It wants to flip, but S1 and S2 are diodes. So it cannot do that. So at that point, S1 and S2 will stop conducting. But I have not provided a gate signal to S3 and S4 yet. I'm providing that at pi plus alpha. So there's no path for the current to flow. So there's no way that the voltage will flip on my load. It's not behaving as a full wave rectifier yet, right? S3 and S4 are not on, right? So, and that's why you would see this, right? So it will follow, it will continue for a while, until when? Until the current becomes zero, like the full bridge rectifier, typical full bridge rectifier. Okay, and we can have some negative voltage. We can have some negative voltage. I'm assuming if you delay this enough, you can make the positive area as big as the negative area probably, and make the average output value to be zero. Simulate it. If you just keep delaying this, if you delay alpha to here, delay alpha until here, right? So you will rise here, and then you delay the next firing signal to S3 and 4 to here, then you will have as much positive as much negative. So your average voltage is zero. Your average voltage is zero, but the current exists, right? So interesting. So is everybody okay with these waveforms? So what happens if I increase inductance to the waveform? Forget about the equation. Waveform. What happens if I increase the inductance? Yeah, which point? This point here will keep shifting to the right, right? It will keep shifting to the right until it hits this point. If it hits this point, what's going to happen? If it hits this point, S3 and S4 now behave like diodes, right? So if they behave like diodes, they will do what the diodes do. They would have conducted and connected the source to the load, right? So this here will be extended all the way to here. Okay? Yes, no? How about if I add a source? It's the same progress, right? So nothing, I mean, the same circuits. So what if I add a source?
It wouldn't start until your current or your voltage of the source was higher than
My source was higher than DC voltage, right? So that's at the beginning, right? But so can I give an alpha anywhere before that? Like if my DC source was up here, does it make any sense? I give the alpha here. I give the firing angle here. It would not turn on, right? Because in this case, the diode itself wouldn't have conducted. So I gave the firing signal, but my DC source is higher than my AC source, so the circuit will not conduct. Diodes 1 and 2, or here thyristors 1 and 2 will not conduct. So as long as your DC source is, the intersection between your DC source and the AC is before the place where you want to give your firing signal, then the waveform looks like what? Exactly like this, right? So let's say the DC source is here. We can look at the slides, right? So this is the continuous current case, okay, right? This is the continuous current case where the inductor was increased, right? So this is the waveform. And then, again, the equation we'll go through next time, but the waveform is okay. Everybody's okay with the waveform, right? And then what this thing is doing is, actually we can talk about that when we're doing the equation. So they're doing the Fourier series for the voltage, and you have a graphical representation of the Fourier series instead of analytical. You will do that in the homework. We'll talk about that next time when we talk about the equations. Yeah. But now I have a DC source. As long as I'm providing the firing signal after the point where the DC source is greater than the AC source is greater than the DC source, so alpha has to be greater than or equal to inverse sine VDC over V maximum, right? So basically, V maximum sine alpha, right? V maximum sine alpha, which is the input waveform. So if this is my input source, and this has a peak value of V maximum, I have to provide an alpha, and I want to provide some delay signal, right? Let's say here. What is the condition? If I want to provide the delay angle here, I have to make sure that I've already crossed this point where VDC is equal to what? V maximum sine theta, right? So the minimum value of alpha is where? I can replace this theta with an alpha, V maximum sine alpha minimum, right? The minimum value of alpha occurs at this point here, right? So you can solve for alpha, it's going to be equal to inverse sine VDC over V maximum. That's where this comes from, right? That's the minimum value of alpha that you can utilize. Besides that, the waveforms look identical. So this is the case where for a large inductor case, the waveform here, the DC value here and the AC value have intersected at this point. So fine, I provided my alpha here. So my diodes S1, switches S1 and S2 have conducted. They've conducted. My RL is very large. My time constant is really large. So if my time constant is really large, the current will continue to flow beyond this point until where? It's a very large inductor to continue until the next set of switches, S3 and S4, receive their gate signal. So the same waveform as the case where without a source. Exactly the same. As long as you satisfy your minimum alpha condition. Okay? Everybody's fine with that? Okay. Alpha, I can, here it's alpha is less than 90, right? And, this area here is the positive area is larger than the negative, correct? But I can keep increasing alpha. Nobody can stop me from increasing alpha. I can make the delay angle here. If I make it here, and then the next one will be here, for S3 and S4 will turn on here. In this case, the negative area is greater than my positive area, right? If my negative area is greater than my positive area, then I've created a negative output voltage, right? So my output voltage is now negative. If I have a negative output voltage across a pure RL load, what's going to happen? If this voltage is negative, and there's no source here, just an RL load, what's going to happen? Negative voltage, negative average value, not instantaneously here, fine. Instantaneously, I had a small negative portion here, for example, and I had an RL circuit, right? But what was my average voltage? It was still positive, right? But what happens here if I make the average value negative? What do you mean by everything? Yeah, the current will want to flip. It will want to flip, right? But can it do that? Look, these are pointing up, right? Are they going to allow the current to flip? They will not allow the current to flip, right? So these circuits, you cannot, if you create a negative average voltage, current will cause the circuit to stop. The current will try to push itself back in these diodes or thyristors and will stop the conduction of current, right? But can we use this to our advantage? Is there another application of it? So we cannot put a passive circuit and maintain average output voltage to be negative. It doesn't make any sense, right? But if I put a circuit with a source here, I connect the circuit with a source, right? And I make this input, my rectification state, provide a negative value, right? Then what can we do? Let's draw that. I have the equivalent circuit of that is before I do that, if the source, if I have a source and current is coming out of my source, what is this doing? It's discharging my source and taking this current and putting it into my load, right? But what if I do this? What happens if I flip the direction of current somehow? Then I'm charging my source. It's like this capacitor I was charging and discharging. Okay, so now I have this nice circuit that I can create. I can flip the voltage polarity, but I cannot flip the current polarity because the current polarity is dictated by the way that these diodes or thyristors are looking up, right? They would never look down, right? So I can do something like this then, right? The current is coming out this way because the current always have to flow in this direction to my load, right? My RL or whatever. And then if I do this, then what's going on? This is my, this is representing my what? my source, my rectifier, and I flipped the polarity of voltage. But I cannot flip the polarity of current because my diodes and thyristors are facing up. Okay, so that will not change, right? So the current will always flow this way, right? I have my RL circuit, does not really matter. This is now doing what? This is now a source, my output, that I can take power from. Remember when current, again, look at this. This is the positive terminal of the source, negative terminal. The positive terminal of the source, current is coming out. What does this do? This is supplying current, supplying power. This is doing what? This is charging this source, right? So what am I doing here? I'm taking now power from my load and pushing it into my source, right? So think of this as a PV panel, right? Just take a PV panel, but you have to flip a polarity, right? So that's you have to make sure that you do this. So you flip the polarity of the panel, so it's providing, you connect it in this fashion, and then you control your full bridge rectifier, SCR-based rectifier, where alpha is greater than 90, so you're able to provide, do this flip as well. And in that case, you're able to take power from your PV panel and pump it back into your grid. Right? Neat? You should try that. Build it. Build it. If I were you, I'd go and build it. So this is the simplest grid-connected PV converter. There are many, many types. Right? People do this. People spend billions of dollars over the past 10 years, or hundreds of millions of dollars over the past years doing research on, better topologies, less ripple, all of that kind of stuff. But at the end of the day, you want to understand the basic concept. Then you want to advance yourself in power electronics and build more complicated converters. That's fine. That's a good thing. But this is the basic, simple concept. Right? Basic, simple concept. The nice thing here in other types of converters, people will have to worry about synchronizing with the grid. Remember when if you did 338, when you had the generator and you want to connect it to the grid, what were you doing? You were doing this experiment. Do you have this lights thing, the stroboscope or something, where you were looking at the shafts being synchronized, or how did you do it? Or was this? Do you just have a meter that says, okay, now they're synchronized, and close the switch?
We have like motors connected. I mean, one motor was connected.
One motor and one generator, okay. And then how did you turn on the switch?
Oh, when it was the green lights.
Yeah, were lights, right? So you had the instrument. What is this instrument doing? This instrument was making sure that before the shafts were connected, that they were at the same speed. Right? Because if you have two shafts, you try to connect them, they're not at the same speed. You will break them up. Right? But if you connect them, they're at the same speed, and then the speed differs. Then one is pulling the other, or one is pushing the other by a small angle. You cannot, there's the load angle. I'm sure Dr. Haytham talked about that. And so that's where the load angle is. Initially, the two shafts come together, but you don't connect the switch until these lights come on. These lights are telling you, okay, they're at the exact same speed. Same speed, and then now you want to deliver power from your generator to or deliver power to the other machine. One delivers power to the other machine. Then if one is a little faster than the other, it will deliver power to the other. So if it's faster, it will deliver power to the other. If it's slower, it will be pulled by the other. Right? So it's the mechanical power is now, you can transfer mechanical power by who's leading the other after that. Right? So same thing here. What gives us a synchronism opportunity in these types of converters? We are synchronized with the 50 Hertz, with our input waveform. Every cycle I'm providing an alpha, right? Every cycle I'm providing an alpha, right? So I have to do it with the same synchronism in mind. It's a different way to synchronize, right? But it's the same idea. In power, other types of converters, you use other ways to synchronize. You use something similar to what you do mechanically, but in electronics, in an electronic way. You look at the voltage waveform on both sides, and then you connect by measuring. Here, I don't need to do that because I'm already my waveforms are already synchronized with the grid. Every 50 Hertz, I have this waveform, right? So this is the simplest PV converter you can think of here, right? So this is when your alpha is greater than 90. Then you're providing this, you're flipping this, doing this flip, providing more negative voltage than positive. And it's called inverter mode of operation. It's a name. Between alpha equals 0 to 90, you're providing positive voltage, or rectifying. So you're taking from your source, pushing to your load. If you have alphas between 90 and 180, you're taking from your load and pushing to your source only, but you have to make sure that your load has the polarity is flipped and it's not a passive load. If it's a passive load, it will not work. Do the simulation. Try it to the passive load. It will start and then stop. Because as soon as you try to put negative current through the diodes, they will, or the SCRs, they will stop. Right? Okay, three-phase. We'll start and then I don't think we can continue. Okay, so we will start the three-phase rectifiers. I will get to some point and then we'll stop. Okay, so let's, to do that, I need to open, I need to look at some pictures. Okay, three-phase rectifiers. I would now like to take my three-phase source and connect to my output. The benefit I saw from the half-wave rectifier to the full-wave rectifier was what? The output for the half-wave rectifier looked like this, with a positive half cycle, and then next positive half cycle. That was the output voltage, right? This was the output voltage of the half-wave rectifier. How about the full-wave rectifier? Output voltage looked like what? Like this, right? Fine. Here the ripple was humongous, right? Here the ripple is also humongous, right? But in this case, I had to choose a capacitor to be able to supply my load for all this time. Here, I had to choose a capacitor to supply my load for half the time, for the same amount of ripple voltage, okay? Half the time. Which is nice, still nice. In three-phase circuits, it's even less. So in three-phase circuits, in every period, I will see in a full-wave rectifier, so this is my period this is one period. For the half-wave rectifier, I see one pulse at the output, right? For the half-wave rectifier. For the full-wave rectifier, I see two pulses at the output. So for the same delta V, I have less capacitance. For the three-phase rectifier, I see 6 pulses in my period. So I will see 6 of those. I will draw them. I cannot draw them. I will draw them nicely later, but you will see them looking something like this. In one period, you will have 6 of these pulses, right? So that means what? My capacitor for the same delta V is a lot smaller, which is nice, because I have these large drives, megawatts power drives, right? I don't want to supply megawatts for my capacitor. I cannot, because the capacitor in here was supplying the load. It's supplying the load right here. All of this time, the capacitor is supplying the load. I don't want a capacitor to store megawatts of energy and supply that to the load. So there's a big advantage in going to three-phase. Other advantages as well, but this is one major advantage. That ripple becomes, for the same value of ripple, you need much smaller capacitors. You need some, but much smaller, right? So that's one advantage here. So let's, I'll start and then we'll stop quickly, okay? I will not, canvas, no, canvas, not white background, file, import. And I want, okay, canvas, white background. Okay, now that's what I want. Okay, so now what do we have? So this here is my VA, VB, and VC. So these are my phase voltages. These are my three-phase voltages: VA, VB, and VC. And these are my line voltages. So this is VAB, and this is VBC, and this is VCA. How do we know that? How do I know I'm not lying to you? Line voltages will lead phase voltages by 30 degrees. So if I have three phase voltages like this, VA, VB, VC, if I want to draw VAB, what is VAB? VAB is VA minus VB, correct? So VA is here, and then VB with a minus sign goes here. So this is VA, and I bring this here, add it to it. So this is VAB. Okay with that? So this waveform here, or this phasor here, is VAB. So if this is VA, this is VB, this is VC, this would be VAB. what do we see? What's the relation between VAB and VA? 214, come on. It's obviously a little longer, right? It's a little longer than this one. If you do the trigonometry, it will be square root of 3 longer than the phase voltage VA. And it's leading it by 30 degrees. We can do the 214 review later. But for now, if you remember from 214 or you don't remember, and trust me,
My 214 class did nothing like any of this.
you did not do any three-phase 214?
Our class opted to do just a little bit of it, but it wasn't required.
Okay. It's fine. We can go over three-phase next time in more detail. We'll go over it in more detail. But forget about three-phase. But for phasor, okay, just for my phasor mathematics. Vector math, okay, this is these two waveforms, VA, this is A and B. I want to A minus B. A minus B will be A, you bring your B here, and then basically add negative B to your A, and this will be the sum. It's obviously longer than square root of 3, and it's leading it, right? So I will go, I will explain three-phase in more detail, but it's leading it by 30 degrees for now. If you do the math or use the geometry, it will lead it by 30 degrees, right? So, or if you just go on PSpice, put a waveform that has a sine wave, phase shift of 0, another sine wave, phase shift of 120 degrees. Okay. Why 120? We can talk about that when I explain three-phase. But just for now, 0 degrees, 120 degrees, two sine waves, and then look at the difference between them. So if you simulate something like this, and measure the voltage here. Put a voltmeter here and measure at these two terminals. This will be VA and this will be VB. Put two sine waves in series. One has a phase angle of 0, one has a phase angle of 120 degrees. Just put them in series. And then measure the voltage across them. It will be 30 degrees leading. So if you look at the zero crossing of the red waveform here, versus zero crossing of the red waveform here. The red waveform here crosses 0, 30 degrees before this red waveform here. Right? So this is the line voltage, VAB, versus this is the phase voltage, VA. Okay? So we'll stop here. Next time maybe I'll go through a refresher of three-phase first, if you did not take it, and then we'll continue with the three-phase rectifiers. I was hoping we get through it, but sure.
So that you get 6 peaks when it's a full bridge rectifier, right?
Well, three-phase full